work out some examples later on anyway, but let's see if we can clarify this. Okay. Okay, let's make this more definite. In other words, we have indexes 0, 1, 2, 3, 4, 5, 6, 7 in this case. Initially, B equals to 0 and E equals to 7. Right. We're only looking at the indexes here. We're not even looking at the values of the elements in the array. The first comparison you can compare against the element at index 3 or index 4. It doesn't matter which one. Let's say we compare against the one at index 3. If the element is larger, if the element is smaller than the value that we are looking for, then what are we doing? We're going to move B so that it becomes 4. Because we want to eliminate everything to the left-hand side of the new B. So B would go all the way over here. The next comparison will compare to the one at index 5. Let's also say that in this case, the element is greater than the value that we are looking for. In that case, E will have to move. But E cannot be here because we just compared to the element at index 5, so that means E has to move one past this element, so E has to be compared, E has to be at index 4. So in this case, once again, B and E are the same, but it means that we have one element left that may still have the value that we are looking for.
So that helps.
Okay, and we will use this exactly this example later on to do a trace, so that we can have a trace that is exactly doing this, but spelling out everything with specific values. So I will keep this one on the board until we have the entire algorithm figured out.
In this case, since B equals E, we still have not evaluated index 4 yet, correct? So
Yes,
we will go through the loop one more time.
Exactly, we have to go through one more iteration, and as a result of that iteration, we will either confirm for sure that the value is not in the array or the value is in the array. But I would still call revision 4 a major revision, because by introducing the variables B and E, we are now capable of expressing, how do we say, eliminate for the first half of the array or eliminating the second half of the array. Now we have a way to express that. And not only that, we also have a way to express when do we get out. When do we know for sure that the value that we are looking for is not in the array at all. So B and E are extremely important in this algorithm. I would say, once you figure out, how to represent the beginning and the end of the array, the rest is more or less tedious, just tedium that you have to deal with. We look at this particular algorithm at this point, and we know we're not done. We know we are not done because, according to the exit condition here, we exit the loop when A bracket M equals to K or B is greater than E. If initially A bracket M does not equal to K and B is not greater than E, do you think doing this conditional statement will eventually cause one of those things to happen? It's not going to cause those things to happen. Well, not always. And the reason has to do with M is not getting updated. If you look at this entire algorithm, which part is updating the value of M? Nothing. Okay? We have not yet specified how we're going to update the value M. So that's one missing piece that is also very important. How do we calculate the value of M to begin with? Because it seems like M is fairly important, but the concept of M is not important. The concept of M is the middle part of the array that may still have the value that we are looking for. Okay? So how do we calculate M before we utilize M? Sounds to me it's just kind of the average of B and E. Right? If you have B and E all the way over here, M is right in between. If you have B and E all the way over here, M is right between. So we are looking at the average between B and E. How do you compute the average of two numbers? You add up the two numbers, you divide it by 2. Exactly. So now we have b plus e divided by 2. But we already know that's going to have a problem, don't we? Because even with the example that we have on the whiteboard with 8 elements, the last index has a value of 7. The first index has a value of 0. 0 plus 7 is 7. 7 divided by 2 is 3.5 or 3.5. Is that a good index to use in the indexing operator? It's not, because it is not an integer. So we have to convert that number into an integer. Sometimes it is, something and a half or something 0.5. The quickest and easiest way to do it is to use what we call the floor function. The floor function is returning the maximum integer or the maximum integer value that is less than or equal to the number in parentheses. Let me say that again. The floor function is returning the integer with the maximum value that is still less than or equal to the number in parentheses. Let's do some examples just to make sure that we know what we are talking about. Okay, the floor of 2.3. What is the largest integer that is less than or equal to 2.3? 2. Yeah, that's easy. What about the floor of 3 itself? 3. Okay. What about the floor of negative 0.5?
0. -1.
Negative 1. Very good. Because negative 1 is the largest integer that is still less than or equal to negative 0.5. Very good. Now, I know this one is kind of tricky, but you don't have to worry too much about it, at least in this algorithm, because b and e should not be less than 0. Okay? By the time they are less than 0, we would have exited the loop already. So m does not actually have to worry about being a negative value. Okay, very good. So we have that initialization. And there's one more thing we have to initialize. If you look at all the variables that we have mentioned here, which two variables are being referred to before they get initialized? B and E. Very good. So we need to make sure that B is initialized before the loop and E has to be initialized before the loop. What is the index of an array? What is the index of the first element of an array that may contain the value k before the first comparison? Has to be 0, right? The very beginning of the entire array. What is the index of the last element that may have the value k in an array?
I plus 1?
We don't have an I here. Bar A bar minus 1. Bar A bar refers to the number of elements in the array. Bar A bar minus 1 is the index of the last element in the entire array. We're almost done here. Almost done. Let's go for revision 6 and finish this up. Revision 6 is just, only has to decide, do we want to use a pre-checking loop or do we want to use a post-checking loop? Because remember, when I use loop and end loop in the evolution of the pseudocode, it simply means we need some kind of a loop. It does not suggest whether it has to be a pre-checking loop or a post-checking loop. So you have to look at this and say, well, does it make... Remember, our preference is to use a pre-checking loop whenever it is possible. Is it possible to use a pre-checking loop here? No, because... Well, you have to look at the condition. The condition relies on m. And when do we calculate m? M is calculated inside an iteration. The first thing within an iteration, we calculate m. So that means we cannot turn this into a pre-checking loop, because if we turn it into a pre-checking loop, what is going to be our m? Well, m is not initialized before the loop, so we can't really use m, in this case. So that means we have no choice but to use a post-checking loop in this case. And that has to do with the condition, the exit condition has to be set by at least one iteration. So we turn this into a post-checking loop. Post-checking loops are easy because all we have to do is to replace loop with repeat and replace end loop with until. That's all we need to do here. And I'll just add one more thing here. I'll just say that we'll go ahead and set a variable called found, and all found is going to do is to reflect whether the element or the value that we are looking for, whether it is in the array or not. It is a way of telling the rest of the program, yes, we found a value, or no, we could not find a value. And that's it. That's the entire binary search algorithm. Yep, go ahead.
How can we still have the else nothing to do option?
Well, it doesn't hurt anything, but you're right. This is something that's just taking up space without anything really without being useful at all. So we can just eliminate else do nothing, because when we do nothing, we can just not mention there's another branch. Okay. Are there any questions about the algorithm itself? Okay. If we don't have any questions, we'll go ahead and trace it.
Why did we change the word loop to repeat?
Because now we know for sure that we need a post-checking loop, whereas before we just know that there's a loop. We don't know whether it is a pre-checking loop or a post-checking loop. So let me make sure that I save the text document first, and I know for sure that I'm not going to be able to create a new folder for some reason. This is 2010, 1018. Now we can save it into that folder. That we can go ahead and create a spreadsheet for tracing this algorithm. I'm not going to spend the time to convert the less than and dash to arrows. I mean, you guys, if you want it to be fancy, you can do that yourselves. So I'll just kind of keep it the way it is right here, so that we can focus and spend more time on the trace itself. And we want to create a test case that mirrors this particular case, where in the end B and E would be the same, and the order of elimination would be the same as the one on the board. We'll go ahead and construct the labels first. We have comments, line number, and then we have our variables. This time we have quite a few. We have B and E, then we have K, we have M, and then we have array A. And if we follow that example, we need a fairly big array. I'll go ahead and do that anyway. So A bracket 0, 1, 2, 3, 4, 5, 6, 7. And we need to give these specific values. 2, 3, 6, 7, 9, 10, 11, and 13. And according to this board here, we're looking for the one at number 4, at index 4. So we want to either look for 9 or something that is close to 9 so that we can confirm that it does not exist. Let's just look for 9 for this round. Okay, so K equals to 9. M does not need to have an initial value. E does not need to have an initial value. B does not need an initial value, because all these items will be initialized as we run the algorithm. So we'll go ahead and optimize the width. I don't think we can display everything. Just barely. Just barely. Once we shrink this one, maybe we can. Excellent. Perfect. Okay, so this is my